Right, in this video we're going to be looking at goodness of fit tests. We're going to be looking at the first ones where we try to do a goodness of fit test of a Poisson model here. Okay, now it's very similar to a contingency table in that we compare observed frequencies with expected frequencies, but we need to calculate the degrees of freedom slightly differently. So we need to look at the number of categories and we need to take away the constraints. And the constraints are anything which are calculated in the question to estimate a variable or what have you. So in this case, we've got 1, 2, 3, 4, 5, 6 columns at the moment looking at it. But one of the things we're going to have to calculate is the actual average rate, the Poisson, the lambda. So we calculate the average rate by going into here and we do 1 times 90, 2 times 55, 3 times 30, 4 times 5 and 5 times 3 to get the total number of computer malfunctions per day, divide by 260 and we get 1.25 as our average rate of malfunctions. So lambda will be equal to 1.25 in this question. Now, when we do this, we need also to state what our null hypothesis is. So our null hypothesis is going to be that the Poisson with lambda as 1.25 is a good fit. And we always assume a good fit for the null hypothesis. And therefore the alternative hypothesis will be that it is not a good fit, okay, is our alternative hypothesis. Now, when we do this, what we need to do is we need to work out what our expected frequencies are. So if we go into our calculator and we go to number 3, our distribution, and we go down to Poisson, okay, and what we can look at is I've worked out the one where x is 5. And here I've put in the x equals 5, lambda is 1.25. Go down, press execute, and the probability of that x equaling 5 is 0.0728619376. And if we times that by 260, we get 1.89. Because there are 260 in total, so the probability times the 260 will give us our expected frequency. And we could similarly do this for 4. So we put in 4 here. Okay, we get 0.29 times that by 260 and we'll get 7.58. Put in 3 here, and we get 0.09. So for this, we'll get 0.09 times 260 will give me 224. Put 2 in here, and I've got 0.22 times 360 will give me 58. Put in 1 here, times 260 will give me 93. So 0.358 times 260 is 93.11. Now, the one thing is, and we can't use chi-squared if one of the groups has a expected frequency of less than 5 values. When that happens, what we do is we group the two together. Okay, we group the two together. So we'll get an expected frequency in here of 9.47, and we're going to call that greater than or equal to 4. Okay, so that's our greater or equal to 4 group. Okay, and we have an expected frequency of 9.47, and observed frequency will be 5 plus 3, which equals 8. And now what we're going to do is we're going to put all of these into a table in the statistics module. So we'll put the 77 and the 74.9 in list 1, list 2. So observed frequencies all go in here, and expected frequencies all go in here. And you can see for my last group, I've got 8 and I've got 9.47, combining these two columns because I can't have an expected frequency of less than 5. Okay, so go from there, and then we're going to look at different hypothesis tests. If you're not in goodness of fit here, you could very well easily have a z-test selected initially. Just go into here, press OK, go down, find the chi-squared test in here, number 3. We want the goodness of fit test. Okay, and our observed frequencies were in list 1. Our expected list frequencies in list 2. Now the degrees of freedom, the way we look at our degrees of freedom, we had basically 1, 2, 3, 4, 5 columns. Okay, so the degrees of freedom will equal 5. But the last column could be calculated because we know all the numbers. Okay, so because we know the frequency, this one is not independent, so we can take away the last column. We also calculated lambda using these values, so we take that off as a degree of freedom to leave us with 3 degrees of freedom. So we put into here the degrees of freedom is 3. And go down, and we're going to put the calculated differences into list 3. And we go down, press execute, and what we get is we get our chi-squared value. So that's our sum of our differences divided by the expected values. So we get 1.9559 for chi-squared, and we see our p-value is equal to 0.581. Now 0.5815, that's 58%. That's much greater than the 5% level. If we test this at the 5% level, that's much greater than the 5% level. So therefore we do not reject H0. Okay, there's insufficient evidence that the Poisson distribution, or shall we just write Po 1.25, is not a good fit. Okay, so always, as always, initially we decide whether we reject H0 or don't reject H0. We don't reject H0, so that, and then we make a real world statement about the Poisson distribution not having enough good evidence for it to not be a good fit. Okay, rather than categorically stating it is a good fit. Okay, and that's how you do a goodness of fit test.